All right, what I want to do for you guys is a continuation of kind of what we saw in the problem review and as to how we solve those problems, but we'll take it a step further and introduce to you kind of a unique scenario. So let's talk about elevators. Let's make sure you can see that as well. In an elevator scenario, basically you're going to get on the elevator. Let's say we get on it at the ground level here. So I'm going to write a person. They're standing in the elevator, and this thing is just at rest. They hit the button to go to the top level, and what this thing has to do is it has to start to move up, which means it has to accelerate. So we're going to give it an acceleration of 1.0 meters per second squared in that direction, upwards. And then elevators don't consistently accelerate. Once they get up to the speed that they want to be at, what they end up doing is that, through a large region, you're going to be moving at constant velocity. Now, what that means is that there's no acceleration here. That's an acceleration of 0. And then once we get to the top over here, we're still moving up, but we need to slow down. That means we need acceleration in the downward direction opposite the velocity to accelerate. So we're going to give it an acceleration of -1 meter per second squared. Now, if we're thinking about the elevator here, there's always a force of gravity acting on the person in the downward direction, and there's a floor beneath them, so there's a normal force acting up. And those are really the only two forces I can identify throughout this whole event here. It's the force from the floor of the elevator, which is the normal force, and the force of gravity. So if I'm looking at the free body diagram of my person, in every single case, we have the force of gravity acting down, and you've got the normal force acting up. And that is it. Now, let's give this person a mass of 50 kilograms, which means that we know his force of gravity is 50 times 9.81. It is 490.5 newtons. So we know his downward force. And let's look at his normal force. A lot of people go, well, isn't the normal force just the same as force of gravity? Sometimes it is, and we're going to find here that sometimes it's not. So when we're sitting here at rest, we know our acceleration is 0. So if we try to apply the second law for this part of the scenario here, let's do that. Let's say that the net force is equal to ma. And what we'll do again is we'll try to represent these two forces in this expression. And this is where we bring the mathematical sign into play. The net force is the normal force, which is pointed up, so I make it positive, minus the gravity pointed down, I make it negative. And here, our acceleration is 0. So if we're doing this expression here, we get a net force of 0, because 50 times an acceleration of 0 would give us 0. What that has always meant is that our forces are balanced. And what we're going to find is that, well, let's mathematically solve for it. The normal force is unknown. I don't know what it is, but the gravity we've already determined to be 490.5. As soon as we move that over to there, we find that the normal force is also 490.5. So essentially, our normal force here matches our force of gravity. And what we do is we typically call the normal force apparent weight. It's basically, how heavy do you feel? Here, we feel like our normal selves because our normal force matches our gravity. You're going to find that sometimes we feel heavier, sometimes we feel lighter. In fact, what ends up happening is that at least when this thing starts to take off, my knees buckle a little bit because I feel heavier here. And then as I ascend, it kind of feels normal. And then when we get to here, what my son does is he tries to jump. And that's what you guys probably do too. Because what it does is it simulates an environment where you can actually jump higher because the floor stops from under you. So you're actually going to feel lighter up here. And we'll see why when we solve for the normal force here. So there's our normal force for before we take off. Now we're starting to accelerate. So let's look at that. Let's apply the second law here. And again, we can represent our net force as the sum of these two forces here. So N is up and gravity's down. This looks identical to this, but now we have a completely different value of A. So when I put in my values here, mass is 50, A is 1, N is unknown, and gravity is still 490.5. When we add 490.5 to both sides, what we end up getting is we get a normal force of 540.5 newtons. So our normal force now is greater than gravity. So this person right here has a force of gravity of 490.5 downwards and has a normal force of 540.5 newtons upwards. Because this is greater than the force of gravity, that's why our person ends up accelerating upwards. It's the normal force that's physically pushing them up. And basically what this makes you do is this makes you feel heavier while this is happening. Now, when you're going up in an elevator, this doesn't actually last that long, feeling heavier, because we get up to speed pretty quickly. And what ends up happening is that we start to coast up in this region here. So when we try to apply the net force again, our normal force is up, our gravity is down, and again, despite the fact that we're moving, we're not speeding up, we're not slowing down. A is 0 here. We're in dynamic equilibrium, which means that we have balanced forces here. So when we put in a value of 0 for A, we get that side being 0. N is this. G is 490. F of G is 490.5. And what you get is a normal force of 490.5 again. So it's no different than when we were at rest. You actually feel normal here as well. You feel like your regular self. On to the very last part, which is where we slow down with a negative acceleration here. So if I do the net force here equals ma, we have N pointing up, F of G pointing down. This expression looks the same in all four scenarios here. But again, it's our A value that's changing here. And we have to be mindful that it's a negative value here. So when I put in 50 for M, negative 1 for A, N is unknown, and the force of gravity is 490.5, what I can do is add 490.5 to both sides. And then what I would get is, on the left, I would get 440.5 as my normal force. So now our normal force is a little bit less than the force of gravity. So you have a net force in the downward direction, and what that's going to do is that's going to slow you down enough to bring you to rest once the elevator comes to rest. So you can go through all these things, and what you find is that you feel normal here, you feel heavier here, you feel normal there, and then at the very top, for that very short instant in time while it's decelerating, you will feel lighter. So hopefully, this kind of provides some insight as to what happens in an elevator. But in addition to that, how we approach our problems. When we can look at our force diagram, we can always set up the Newton's second law expression and add one more line to it involving our forces and their directions. And then that'll help us solve things. But the really new thing that we saw was that we had to put in the negative value of A here in order to figure out what our unknown force is. And then it got a result that makes conceptual sense to us.